Hello, this is Tim Smith, the Academic Support Coordinator for St. John's River State College, St. Augustine campus. This video, Asymptotes, is designed as a study aid and supplement to the math tutoring services offered at St. John's River State College. In this video, we will be discussing the definition of an asymptote, asymptotes of inverse functions, asymptotes of exponential and logarithmic functions, and oblique asymptotes. The line x equals a is a vertical asymptote of the function y equals f of x if y approaches positive or negative infinity as x approaches a from the left or right. The vertical asymptote of the function is related to the domain in that if x equals a is a vertical asymptote, then the value a cannot be within the domain of the function. The line y equals b is a horizontal asymptote of the function y equals f of x if y approaches b as x approaches positive or negative infinity. The horizontal asymptote of the function is not always related to the range. If y equals b is a horizontal asymptote, b may, for some functions, still be in the range of the function. Let's start with the function f of x is equal to 1 over x. This is the simplest function that contains both a horizontal and a vertical asymptote. The mathematical inability to divide by 0 creates these asymptotes. The domain of this function is on the interval from negative infinity to 0 and from 0 to positive infinity. The domain excludes 0. The vertical asymptote occurs at x equals 0. The range of this function is likewise from negative infinity to 0 and from 0 to positive infinity, again excluding 0. The horizontal asymptote occurs at y equals 0 because as x approaches plus or minus infinity, 1 over x approaches 0. Functions of the form f of x is equal to ax plus b over cx plus d, where a, b, c, and d are integers, may be graphed as a transformation from the original function f of x is equal to 1 over x. In this case, a vertical asymptote may be found by setting the denominator equal to 0. We then put the function in the form a plus b over cx plus d. In this form, a represents the horizontal asymptote because b over cx plus d approaches 0 as x approaches plus or minus infinity. As an example, let's find the horizontal and vertical asymptotes and graph the function f of x is equal to 2x minus 3 over x minus 2. The vertical asymptote happens when x minus 2 equals 0 or at x equals 2. To find the horizontal asymptote, we divide all terms by x. In the first term of both the numerator and denominator, the x's cancel, leaving 2 minus 3 over x all over 1 minus 2 over x. As x goes to plus or minus infinity, 3 over x and 2 over x goes to 0, leaving 2 over 1, or the horizontal asymptote y equals 2. With the asymptotes established, the graph may be sketched identically to 1 over x. Next, let's discuss exponential and logarithmic functions. F of x is equal to a to the x for all a greater than 0 and not equal to 1. The domain is all real numbers and the range is all numbers greater than 0. This means it will have a horizontal asymptote at y equals 0. We can show this with the graph of e to the x. For f of x is equal to log base a of x for all a greater than 0 but not equal to 1, we have a domain that includes all real numbers greater than 0 and a range of all real numbers. This gives us a vertical asymptote of x equals 0. We can show this with the graph of the natural log of x. Since exponential functions have only horizontal asymptotes, only vertical transformations of these functions will change the asymptote. For example, let's evaluate 2 to the x. The domain of this function is all real numbers, and the range is all real numbers greater than 0, where the horizontal asymptote at y equals 0. In this case, a vertical transformation such as 2 to the x minus 2, the domain remains unchanged, but the range changes to all real numbers greater than negative 2 and moves the horizontal asymptote to negative 2. Conversely, Logarithmic functions have only vertical asymptotes, so only horizontal transformations will change these. The function log base 2 of x has a domain of all real numbers greater than 0 and a range of all real numbers, making a vertical asymptote at x equals 0. The asymptote of this function is affected by horizontal transformations, such as g of x is equal to log base 2 of x minus 2. This changes the domain to all x's greater than 2 and moves the vertical asymptote to x equals 2. If r of x is equal to p of x over q of x is a rational function in which the degree of the numerator is one more than the degree of the denominator, we can use polynomial division to express the function in the form r of x is equal to ax plus b plus r of x over q of x, where the degree r is less than the degree q and a is not equal to 0. This means as x approaches positive or negative infinity, r of x over q of x approaches 0. So for large values of the absolute value of x, the graph y equals r of x approaches the graph of the line y equals ax plus b. In this situation, we say that y equals ax plus b is an oblique asymptote. For example, let's evaluate in graph f of x is equal to x squared plus 2x over 2x minus 2. The vertical asymptote is easily determined by setting 2x minus 2 equal to 0, or where x equals 1. This function has a second degree polynomial for the numerator and a first degree polynomial for the denominator, meaning it is likely to have an oblique asymptote. If so, we can complete the polynomial division to arrive at a form that displays the equation for the oblique asymptote. We write the dividend with a 0 for the constant term, or x squared plus 2x plus 0, divided by 2x minus 2. The first term will be x over 2 times 2x minus 2 equals x squared minus x. Subtract to get 3x and bring down the 0 term. The next term will be 3 over 2 times 2x minus 2 is 3x minus 3. Subtract to get the remainder of 3. Therefore, x squared plus 2x over 2x minus 2 is equal to x over 2 plus 3 over 2 plus 3 over 2x minus 2. The oblique asymptote is then the line formed from the equation y equals x over 2 plus 3 over 2. Let us next gather a few test points. F of 0 equals 0. F of negative 2 also equals 0. F of 2 equals 8 of 2, or 4. F of 3 equals 15 over 4, or 3 3/4. And F of 4 equals 4. We now place the test points on our graph 0, 0, negative 2, 0, 2, 4, 3 3/4, and 4, 4. We can now sketch the graph with some degree of accuracy. If you have further questions on this or any other math topic, or wish in-person tutoring, please consult the Academic Support Coordinator on your respective campus. Thank you, and good luck with your studies.